So this exercise concerns actually dimensionality reduction, all right, by using PCA, and how we may visualize a principal component projection of space, some things about correlation, and some things about clustering analysis. All right. So uh, our analysis here is going to be on to the empty cars dataset, which is available in our library. Okay, so according to this exercise, we are going to go through all these, let's say, questions, right, or tasks. Okay, so I'm going to start. This exercise is adapted from James et al. Book. All right, so, okay, so I'm calling this, right, to get some information concerning the database. All right, so it has 11 numeric variables, right? The first one is the miles per gallon, the number of cylinders, the displacement, the horsepower, uh, rear axle ratio, okay, the weight, um, and I'm going to tell you what is important, the type of engine, and the transmission, automatic or manual, the number of gears, and the number of carburetors. All right. Okay. So I'm going to go back. So we got an idea of the. So we may just call data. Okay. Just to have them instead of calling them. And we may just trying to create uh, the PCA transformation, right? So for applying PCA, we need just to uh, actually transform data so that they are having zero mean values and unit variances. So we are just calling this and create this new project data here, right? All right. And we may just want to see what this new object has, right? Okay. We may just display the center of the centroids, actually, okay, of the attributes in our original space, okay. And we may just see the scaling function factors if we have ones. Of course, we are going to have, because uh, data are right now normalized so that they have standard deviation of 1, right? So this is a second transformation of scaling the original axis, right, by these factors, okay? And after that, we are going to see if we have some rotations. Of course, we are going to have rotations because you see what are the rotations. So what are these PC1 and PC2? These are the principal components which are created, which are actually the new axis in the new principal component space, let's say, and these are actually the rotations of the former axis to coincide with the new ones, right? So the transformations are actually uh, a translation to move data to have some kind of zero, the new origin lies in the center of mass of the data. We are having some scaling to normalize actually the values of the data. And after that, we are having uh, rotations so that the data are presented in the new, let's say, frame of reference, the principal component frame of reference. All right. So after that, we may just trying to see what are the variances and the standard deviation, right? So we are going to do some kind of let's say calculations. But all right, before going to that, you see that these are the let's say the parameters. So if I go back and see that these values here, what is actually meant by this is that principal component one is a mixture of the former attributes, and you may see that these are the coefficients of the linear relationship between the PC principal component one, the first component, and the former ones. So if you take these coefficients, you may create something like that, right? So these are the contributions of the original attributes to the new principal component one attribute, right? So this is a linear combination of the older one. Okay. Right now we are going to just trying to, let's say, find some values um, which are going to show actually the contribution of each principal component to the let's say the whole variation of the system, right? Okay, so I'm going to just call this. So in the first place, we're doing some kind of statistical analysis data. So these are the deviations, okay? And these are the variances. Right? So which are actually the standard deviations squared, okay? So these are kept here, right? and we may just see them. But these are the values. And after that, we may just call this, and this is actually the contribution of each variable to the summation of the variances of the variables. So this is a, let's say, a vector. Let's try to calculate it and just displaying it. All right. So what this says is that, okay, the contribution of PC1 of the principal component 1, so the variance of this divided by the variance, the whole variance of the system, is actually 60%. So this means that principal component 1 incorporates the 60% of the whole variance of the data. And the second one, 24, and the third one, 5. So up to here, with the three first principal components, we have gone up to 90%, almost 90% of the variance of the system. So if we are just keep only the two principal components, we are incorporating in the system and get rid of the rest, all right? So we are just incorporating in this new representation of the data almost 90% of the variance of the original data, right? So somebody may just decide to get rid of the rest and just keep only the first three principal components, which are linear combinations of the original ones, and just right now the data live in a three-dimensional space. All right? So this is the idea. Okay, so we may just want to plot them. All right, so this is, all right, I'm not going to do this. I'm just trying to present this. All right, so you see, this is the first principal component. This is the 60% that we have seen. This is the 24. This is the third. All right, so these are the variations of the principal components. All right, so if you add up them, you create something like this, which is the cumulative PV. All right, so we start with 60, right, for the first component, and if we add this 24, we go up to 84, and if we add this one, we go up to 90. You see that this is 90 for the three first principal components. So if we add, we go up, 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 up. And of course, if we add all the principal components, we add up to 100%. All right. But sometimes we decide that, all right, that let's say 4 or 5 or 6, let's say, components which go up to 95% of no, 96 or something. All right, we may just have the specific value, but by this chart here, we are just saying, all right, 6 principal components incorporate almost 96% of the initial variance of the data. So we may just keep only 6 and get rid of the rest. All right, so this is how we do dimensionality reduction by using PCA. All right. So in terms of visualization, all right. So we just maybe we just want, because right, our space, our presentation space is two-dimensional, is to keep only the first two principal components, which in our example just incorporate almost 84% of the initial variance of data. All right, somebody says that's good enough, all right, and maybe it's good enough for visualization purposes. So we may just use this biplot here, right, and see what we have. All right, we're having something like this. So this is the representation of the new space, of the new principal component space in a 2D dimensions, in a two-dimensional space. All right, so, but all right, this diagram is not very readable, so I may just use another one which comes from this library, which I think I do not have it, but so I think that I'm gonna need to, yes, all right. So I may just install packages to what do I have? So I have, yes, I just forgot the quotes. I can live with it. All right, so I select Greece, let's say. All right, I think I'm ready right now. Okay, let's go back and try to load the library. All right, library is loaded. Okay, and I may just use the first. All right, you see that this is much better than the former one. It's more readable. You may just see the vectors of the initial attributes, and the data are, let's say, more easily. You have the grids here to understand what you are viewing. You have this is the first principal component, which actually incorporates 60.1% of the data, and this is the second principal component, which incorporates 24 of the whole variation of data. And all right, so this is a very good depiction of the data. So this is let's say, a projection of the data onto the two first principal components that the PCA actually created. All right? Okay. So what else can we do? Is all right. So this is the depiction. Right. Right now we may just try to find the correlation, right, between the data, right? So I'm gonna just call load library for my correlation. All right. So I'm just using the correlation chart that I have already shown you. So I just save the correlation data onto a new variable, this correlation matrix. All right, and of course I'm going to let's just do this and check what I have. You see, these are the correlation coefficients. If somebody wants to see them in a numeric fashion, all right? Okay, and of course we may just depict this in some kind of chart, all right? And I'm going to use this function here, all right, and see this is all right. This is the correlation coefficient map, all right. Of course, if you want here, I have not included in my solution here, but all right, you see that, all right, I have just highlighted here, I have circled the higher, let's say, correlated data here, right? So you see that cylinders and displacement are highly correlated, and here displacement and weight maybe, all right, and I don't know, and horsepower and carburetors, and all right, so these are negative correlation values, right? So cylinders and MPG are correlated negatively. So if one just rises up, the other one goes down, right? Okay. And what we may just get here, right? I'm going to use this because, all right, I cannot do it in the R environment here. All right, if I want to, let's say, somehow interpret, you see, the carburetors and the horsepower, which are correlated by this factor here, you see that these former vectors, former axes, are close to each other, which means that, all right, if you move something on this axis, actually is moving by 75% on the other axis. So this actually correlation shows somehow the angle between the two, let's say, axes, right? And here I'm having what I have a high correlated between cylinders and displacement by 90%, which is this one, right? Displacement and cylinders. Actually, you see that these vectors, right, having a very low angle between them, right? So, on the contrary, if we go and see this axis MPG with, let's say, displacement or cylinders, I don't know, this value is minus 87%, all right? So minus 87 is this one, right? And 85 is this. So MPG is reversely correlated with weight, right? So you see that actually these two vectors are opponent, right? Okay, and this vector is opponent to HP. So what is this? This is VS against VS against cylinders, right? 81 minus. Okay, so this is how you see how these values are correlated and how you may interpret this correlation by seeing this kind of presentation of the principal onto a two-dimensional principal component space. All right, so this is how you may understand what you are seeing, otherwise there is no meaning, all right? Okay. And here is a summary between the for the principal components, the standard deviation, and all right, some other values. All right, right now we may just want to do some kind of clustering, let's say. So I omit this, and I am just going. I don't know if I have something better. All right, I'm going to use this heat map presentation and try to do this clustering. Okay, all right. So I think that I need this superheat library, but I think that I have not installed it. So I need to install packages. All right, and just try to install this super library. All right, it is already installed. Okay, and I'm going to use this function here to create this heat map with a dendrogram which shows the relationships between the data items that I have. All right. Okay, let's try to do this. What? Could not find. All right. Okay. Of course, I have installed it, but not loaded. Library. Super. Okay. Hit. All right. And right now I may just copy once again this and use it here. Right now it's gonna work. All right, so this is the result. Okay, so this is the result. You have a dendrogram here, all right? And these are the heat maps for the specific attributes. So what the heat map just gives you is that just by viewing the colors, so here the Viridis, let's say, color map is used. All right. So by just viewing the colors, you may just identify which items are similar to each other, right? So you see that these have almost the same color, so there is a similarity here or here. And also here you are seeing by this that this datagram has found actually the relationship in the first level, then in the second level and third level, and right by creating a tree here. And so this is the root of the tree. So how can we do clustering? By using this kind of tree, right? And of course, just using the correlations between these items, the attributes that they have. All right, so I may just return here because I have the example here. I cannot do it in the so you may just decide that you want to create 4 clusters. So it's just like by cutting this here, right, this tree, and say, all right, so this is the first cluster, this is the second, this node, this tree node actually uh, is the root of the second cluster. So the second cluster has all these occurrences, all right? And the third cluster here has all these occurrences. And the fourth one has all these occurrences. So if you do that, so you just have these clusters, all right? And if you go back to the uh, PCA presentation, the principal components, the first two in a two-dimensional space, and try to identify the clusters, you see that the first cluster is this one, the second cluster is this one, and the third is this one, the fourth is this one. So I think that this is a very good job of clustering, and you see that, all right, this is quite a good outcome. All right, okay. Um, so this is, sorry, this is for the first two PCs, and this is clustering 4 classes from the hierarchical cluster on the whole data set, all right, without doing the PCA analysis. Right, so you see that this clustering on the whole data set, right, by using all the variance of the data that we have is this clustering here. And by using only the 2 first principal components, we have this kind of clustering. All right, so there is some kind of different, let's say, clustering, all right? So this red cluster has, let's say, uh, it's been enlarged somehow and just included these 2 items also, and the fourth one is actually contracted in only these items here, you see, all right, so, but, and this one has lost these 2, which are included in this third one, right? So this is how things work when we are just trying to use. We may lose something, but we may earn something. And of course, it is somehow discussable, let's say, if these 2 belong to this cluster or belong to this cluster, right? So, because sometimes some of the data which are on the let's say on the lower principal component of values may be considered noise. So what I mean is that, all right, or outliers or whatever. So we do not know beforehand if, let's say, if we are having this distribution here, you see, if these principal components contain combination of the original data which have information or they are just having noise, right? So the question is, can we get rid of this or not? Or so more or less, actually, experience says that, all right, we may just uh, do principal components on whole data, right? Like this one, and do clustering on whole variables. So this is for the whole data set. And this is for only uh, the first two principal components. So we may just try out to see what if we have six principal components, or maybe four or eight, or maybe the principal components which actually represent the 90% uh, of the um, of the variance of the original data, and see what happens. All right. Okay. So there is much of some kind of experimentation of how we can just deal with these things on the data that we have, right? Okay, so this is for the whole group, right? And this is for the first two pieces. Okay, all right. I think that's all for now for this exercise. You may just try the exercise by your own and do your own uh, experimentation and see what happens, right?